Cool. So today we're going to talk about forces, and in order to talk about forces, okay, so today's homework will be your phase 1 from both your forces and your work and energy, so chapter 2 and chapter 3 within your physics 1 workbook. Okay. And then you do one of the passages from chapter 1. That was in phase 2, or you can do the phase 2 from chapter 1. Does that make sense, Sophie? Awesome. Thank you for understanding. Let's get started. So today we're going to talk about forces. No, don't want to end the meeting. So when we talk about forces, we need to introduce Newton's laws. There are 3 laws. The first law, often referred to as the law of inertia, simply states that objects at rest remain at rest, and objects in motion remain in motion at a constant velocity unless acted upon by a net external force. Okay. So what does that mean? So when I think of Newton's first law, I like to think of an example where I'm riding in an elevator. So when I first move up in the elevator, I feel a little bit heavy, right? That's my inertia trying to remain at rest. And when I get to the top floor of an elevator, right, I feel a little bit lighter, right? That's my inertia trying to remain in motion. In both cases, though, I have a net external force of gravitational force pulling down on me, okay? So objects at rest remain at rest, and objects in motion remain in motion at a constant velocity, unless acted upon by a net external force. Okay, so this is the rule that governs all motion, actually. So the next law, Newton's second law, this is the one that we're going to be applying a lot today. It simply states that the sum of all the forces acting on an object is equal to mass times its acceleration. The units for force is kilogram meters per second squared, otherwise known as a Newton, denoted as capital N for short. Okay. So when we talk about Newton's second law, we're talking about the sum of forces acting on one object. Okay. So sum of forces acting on one object is Newton's second law. And we're going to be doing this again and again and again today when we talk about forces. Okay. The last Newton law that you guys need to know is Newton's third law. And Newton's third law simply states that for every force or action, there is an equal but opposite force or reaction. And the perfect example of Newton's third law is when two objects are in contact with each other. So right now, you guys mostly, for the most part, are either sitting on a chair or standing on the ground, right? In both cases, there's an equal and opposite force that acts from the chair or from the ground that opposes your gravitational force or your weight, right? That's your normal force. So whenever two objects are in contact with each other, Newton's law of equal and opposites come into play. So for every force or action, there's an equal but opposite force or reaction. So, right, if you think about it, you're sitting in the chair, Newton's first law says you should be falling down, right? Because there's a net external force acting on you. The reason you're not falling down is because there's another force, there's an equal and opposite force from the chair or from the ground that's pushing back up on you, which we call normal force. Okay.
He hasn't been able to call it in. It is on his desk.
Sorry, I had to mute a student. Any questions on Newton's laws? All right. So let's think of an example. If we have an object like a book on a desk, and we're pushing that object to the right with some force, we're going to give it what we call an applied force. There's also two forces that are acting on it. We have its weight and the normal force, which is coming from the table, right? This is its equal and opposite force. So this force and this force should be the same magnitude and in opposite directions. So if we push this object, like your book on the table, Newton's first law says it should continue moving in one direction, right? It should be moving and continue moving, but it doesn't. It comes to a stop. What's acting on it that'll cause it to come to a stop? Very good. The detail. Friction. So frictional force, force of friction, is acting on it to cause it to come to a stop. So let's take a look at friction. So there's two types of friction that you guys need to know. The first is your static friction. The second is your kinetic friction. So static friction is when an object is staying still. The maximum static friction is simply the coefficient of static friction times the normal force. Notice I say it's a maximum. So this is the maximum threshold that you need to reach before your object begins to move. So like imagine if you're trying to push anything, right? You have to put a lot of force in to get it to move because you have to overcome this static frictional force that's acting against you. This term here is called mu sub s. It's called the coefficient of static friction. Okay. The units for friction is still some unit of newtons, but this is the equation for static friction. For kinetic friction, it's simply mu sub k times the normal force, n being our normal force. By the way, normal force is always perpendicular to the resting surface. So no matter where you're at, or what angle that you have, you're always perpendicular to the resting surface. Okay. With kinetic friction, this is when the object is in motion. And mu sub k is called the coefficient of kinetic friction. Both are experimentally derived terms between a surface and surface interaction. You typically do that in like material science class, where they take two surfaces, rub them against each other, and figure out the resultant frictional forces due to those surfaces rubbing. Okay. So the units is friction. This is for friction. Okay. You have static friction and you have kinetic friction. Keep in mind, would kinetic friction be the same regardless of applied force? Yes. Typically, they're given to you. It's rarely that you have to calculate it between surface to surfaces. In real life, there's an actual whole book that you can look at the surface to surface interaction to find your mu sub s and mu sub k. These are constants, like I said, experimentally derived from a material science perspective, and where you're rubbing surfaces with each other. And so, yes, mu k, what I'm going to get to in a little bit, was mu s is always greater than mu k. So since mu s is greater than mu k in real life, static friction, so the amount of force you have to push to get an object to move is way harder and greater than it is to get an object that's already moving. And if you ever had your car die on you and you had to push it, trying to get that car moving when we first start pushing, it is the hardest, right? But the second it has motion, then it's really easy to just keep it moving. Okay. So that's the difference between overcoming static friction and kinetic friction. And when we're dealing with the ideal MCAT physics world, they can equal to each other, but that only happens when you're in ideal MCAT physics land. Most of the time, mu s, actually in real life, mu s is always greater than mu k. So one of the students asked if with kinetic friction, if it actually follows Newton's third law, and it doesn't. So if you're pushing with a force great enough to overcome mu s, then that force, that applied force that you're using, is going to be greater than mu k. So therefore, you just then subtract it, then you have a net force, and you apply Newton's second law, and you get an net acceleration for your object, right? So if you think of your vehicle when you are hitting the gas, right, the force that you have driving your engine and driving the wheelbase and the crankshaft forward is going to be greater than your frictional force that's acting on the ground. Okay? And that's how you get a net acceleration moving forward. Good questions. All right. Now that we've introduced all that stuff, let's take a look at a typical force problem, learn to deal with it, and look at that object. So let's say we have, first problem of the day, we have an inclined plane with an object of mass m at rest on it. What we're going to do is increase the angle. So I want to know what is the maximum angle that I can increase that inclined plane before the object begins to slide. Units are, or my hint to you guys is that mu s exists. So what's going to happen is, here's your inclined plane. We're going to increase this angle until that object that's at rest on that inclined plane with some mass m is going to begin to slide. So find me that maximum angle just before that object begins to slide. Want to get you guys to get your feet wet, thinking about force problems again, and then we'll go over the methodology and how to approach any type of force problem. So first step, we draw a picture, which I've already done. So the next step should be drawing all the forces that we have on this. So what force do we have still? We should still have technically the same forces that we had acting earlier on that book example that I gave you, right? The book example being this example, right? Where we're pushing it, there's normal force, there's weight, and there's friction. So, what forces do we have on this object? Ask yourself that, and then draw the forces. Is this object still resting on a surface? Yes. Newton's third law still applies. It has a normal force. Draw that normal force. Is it still here on Earth? We still have gravity acting on us? Yes. So you should be able to draw that vector. They're going to be equal, Mo, not greater than, right? Because we're just before it begins to slide. If it was greater than, it would be sliding. So with these force problems, first thing we do is draw a picture. Next thing we're going to do is draw the forces acting on it. So we need to draw our weight, our normal force, and our frictional force. Okay. Then we need to select an appropriate coordinate axes. I want to select X to be along the direction of the incline and Y to be perpendicular to the length of the incline. The reason being is if I do that, both the normal force vector and the frictional force vector along my X and Y axes appropriately. And so the only vector I need to break down in components is the weight vector. So we need to break it down into a Y component and we need to break it down into an X component. Okay. So my question to you guys is, where is this angle theta in this new right triangle that I just made? Is it in the upper half here, or is it in the lower half here? Okay. I'll go with the first person that answered upper. Aditya, why upper? Please explain. Feel free to talk. Why did you say it was the upper angle instead of the lower one? Okay. Who's next? Intersecting. Tiffany, you want to explain why you said upper? Because you were next after Aditya.
I just looked at all the angles supposed to add up to 180. So this is like 90, and this would be like 90 minus this, And then
Uh-huh.
both of these add up to like 90. So that's how I figured out this equals to this.
Genius. That's how I would have done it. Very, very good. Thank you. So, basic geometry. What Tiffany said, right? Remember that the sum of the angles in a right triangle add up to, or any triangle add up to 180. We know that this is 90 degrees, this is theta, and this is 90 minus theta. And we know that this is also a right angle right here. So that means this has to be theta. So now that we know that, we can break the weight component or weight vector into components. So this is going to be mg sine or cosine. This is the adjacent side. Cosine, very good. Cosine is adjacent over hypotenuse, and sine is opposite over hypotenuse. So this is going to be mg sine of theta. Okay? So, net effectively, what have we done? We've taken a problem that is on an incline and made it to a problem that's horizontal. So this is going to be mg sine of the angle. We have mg, the cosine of the angle, going down. We have normal force going up, and we have frictional force, which is what? Mu sub s times n, right? So now we apply Newton's second law. So some of the forces in the x direction, some of the forces in the y direction. So in terms of x and y, it's just right minus left, right? So what's your right facing force? Yeah. Mg sine of theta. Thank you, Stephanie. The leftward facing force is going to be your frictional force. That's equal to mass times acceleration. But in this case, this is before begins to slide, which means what for acceleration? It is 0. Does that make sense? Now we do the y. We have normal force minus mg cosine of theta is equal to mass times acceleration in the y direction. Once again, before the object begins to slide, so acceleration is equal to 0. So, normal force, so you have, if you think about it, you have two equations, two unknowns. You don't know theta and you don't know n. So then we can solve for n using the second one, plug it into the first one. And we can see that it's going to become mg sine of the angle minus mu s mg cosine of the angle is equal to 0. So move it to the other side. Mg sine of the angle is equal to mu s mg cosine of the angle. Right? No longer equal to 0 because you moved it, added to the whole thing to the right side. So we divide throughout by mg. That becomes 1. You can divide throughout by cosine, so you get sine over cosine, which is tangent is equal to mu s. So theta is simply the inverse tangent of mu s. Okay, so this is how you handle most force problems. And we were going to go through the steps and how I did it. Even though I just explained it to you, we're going to make sure that we understand. Anyone have questions on this before I move on from this slide? Okay, so let's look at my force problem recipe. So whenever I deal with any type of force problem, I'm doing these steps. First step is I draw a picture. picture says 1,000 words. I can't stress it enough. Be able to draw the situation that they've given you. The second thing is I need to draw all the forces acting on that object, otherwise known as a free body diagram. So we have draw a picture, draw the forces acting on the diagram, all the forces. Third, what did we do next? We selected an appropriate coordinate axes that we have available. And for our problem in the previous one, our coordinate axes was perpendicular to the incline, and this is parallel to the incline. Sorry. Any questions on that? Fourth thing, break up any necessary vectors into components. This is so we can look at what we need to be able to select an appropriate coordinate axes and then match it up so that's up minus down, right minus left in terms of your x and y components with each other to find the resultant vector. And last but not least, we're going to apply Newton's second law. Okay. So we're going to sum up all the forces, set it equal to MA. So these are the 5 steps that I just used to solve this problem. So whenever you have any force problems, make sure you try to go through these steps. These steps will guarantee that you get it right 100% of the time. This is very similar or analogous to the guess method that I had you guys do for your kinematics. Okay. All right. So next thing that we need to know. Second problem to you to practice this force problem recipe. So this is some angle theta. We have an object of mass 2m connected to a massless string and pulley system. It's going over, and at the other end, it's staying stationary with some object of mass m. So I want you to find me this angle so that this whole system is in static equilibrium. So give me a number for that angle. Should be able to do that. Apply your force problem recipe. You can't stress that enough. If you have questions, feel free to text me. Yes, for those who've gotten it, thanks for participating. Please wait patiently so that everyone gets a chance to try it. I want to make sure that everyone gets on the same page. So, like we said, draw your picture, which I've already done for you. Now draw your free body diagram, which is drawing all the forces acting on that object. Remember that if something is resting on something, there's such a thing as normal force. I'm going to tell you that this ramp is also a frictionless ramp. Another minute or so for those who are still working. All right. So what are the forces acting on the 2m mass? You have to be able to label real forces. We've introduced quite a few today. We talked about normal force, we talked about weight, we talked about friction. Yes. We have normal force, gravity, and correct, tension. So we have normal force, which is perpendicular to our resting surface. We have gravity, which is straight down, which is the mass times the gravitational acceleration constant. And we have tension. So both normal force and tension are along the axes we're going to draw. Yes. Michaela, if you go back and look at normal force is always perpendicular to resting surface. Okay. So no matter where the resting surface is, if it's a vertical resting surface, the normal force is horizontal. Make sense? So in this case, it was perpendicular, and then it's going to be perpendicular again. Cool? So this is your y, and this is your x for selecting an appropriate coordinate axes. So then we can break this into components again. And theta is always on the upper end of that right triangle. So then this is 2mg sine or cosine? Very good. Still the adjacent side. 2mg sine of the angle. Okay? So if we look at the 2m mass, the sum of the forces are in the y direction is simply normal force minus 2mg cosine of the angle is equal to mass times acceleration. And this is 0. It's in static equilibrium, i.e. static means not motion, not in motion, staying still. Now we do the sum of the forces in the x direction. I'm going to choose going 2mg sine of theta to be positive minus the tension is equal to 2m times a. By the way, this is 2m, not m. But in this case, acceleration is also equal to 0 because it hasn't started to move yet. Let's draw the forces on the single mass hanging by itself on the right-hand side of this pendulum problem. So, what are the forces there? Is it resting on anything? Careful. If it's not resting on anything, there can be no normal. Very good. Exactly. So there's just tension and the weight of that object. So if it has mass, it has weight. If it's connected to a string, the string probably has tension. So just safe bet. So if we look at the sum of the forces in that case, sum of the forces in the y here is equal to tension minus mg is equal to ma. This is 0. So we have two unknowns. We don't know the angle, and we don't know tension. We can solve for normal force in terms of the relative angle. We don't know this. So let's solve for it. Notice that if an object is frictionless, what do we not need to worry about? We don't need to worry about the x component, the y component in the inclined plane section of that problem. Because if you think about it, when we did the problem before, what did we use this equation for? We used it to substitute in to find friction. If it's frictionless, we can basically ignore this whole f of y equation. So, since we're ignoring that, we end up getting 2mg sine of theta is equal to t, and t is equal to mg. So we can write that here like this. Bring over the divide throughout by mg. That just becomes 1. Divide by 2. So sine of theta is equal to 1/2. So theta in this case is equal So let's go back to the force problem recipe. What did we do first? We drew a picture. What did we do second? We drew all the forces acting on the object. Based on those forces, I'm going to choose an appropriate coordinate axis. So if we are choosing an appropriate coordinate axis, I chose this to be my y and this to be my x. The reason being is normal force is already in the y direction and tension is already in the x direction. Are we good with that? Good. Then the third step that we did, the fourth step that we did in the force problem recipe is we're breaking up vectors into components along that new x and y. Since this weight vector, which is downwards like this, is not along this x or this y direction, I need to find vectors that are along that x direction, like this, and vectors that are along the y direction, like this. So I'm breaking up my weight vector 2mg into a new y direction and a new x direction that matches our new coordinate axes. You can break it up the other way too. It'll be the same thing. Theta is just now here in that right triangle. Tiffany, was it Tiffany? I think Tiffany was the one that explained it last time. So if we go back to the last one, it's a lot easier to see. This was 90. This is 90 minus theta. We're good with that, right? This forms a right angle. This has to be theta. Did that answer your question of why we know where to put theta?
Yeah, I did hear.
So the same thing applies here, right? Let me erase all this other extra noise that we put in. So same thing applies here, right? That's theta. This is 90. This is 90 minus theta, right?
Mhm.
This is theta because this forms a 90-degree angle.
Oh, okay. That makes sense. Thank you.
Yep. It's good. Other people were voicing the same thing. So does that make sense? Does that make sense?
And then I was also just gonna ask, how do you know which side is cosine and which side is sine? Like I know SOHCAHTOA, but
Yeah. So what does SOHCAHTOA stand for?
well, sine's opposite over hypotenuse.
So what side is this from the angle? Is that the opposite side or adjacent side?
The sine or the green line is opposite.
Correct. So that's why it's
Sine. Okay.
and the blue line is adjacent.
Adjacent.
So
It's
that's why.
cosine.
There you go.
Okay. Thank you.
Yep. That's what we're using SOHCAHTOA for. So all that stuff that we talked about decomposing vectors last week, we're still applying it this week, right? It hasn't changed, right? So we got to keep all that knowledge that we had before back again. Jonathan, just be sure tension is 0 because of frictionless surface, correct? Incorrect. Tension is not 0 here. Tension just cancels out. That is correct, Tiffany. So notice if we drew this problem horizontally, Jonathan, this is 2mg, this is your rope, and this is the other m on if I stretched it out. Fy is 0 because if you think about it, have you ever gone down an inclined plane and then just jumped up all of a sudden? Like you say you're going down a slide. Do you ever have any vertical or perpendicular motion when you're going down an inclined plane, like a slide? Hardly ever. Like never. That's because there's bumps, Sophie. Yes, there's bumps on the hill. But if the hill was straight, like those groom paths, bunny slope, I doubt that you're going to be jumping. We're not talking like double black diamonds and black diamonds or even blues, right? There's mountains on those hills. But if you're going down a typical slide, because that's what this inclined plane is, right? It's like a slide that kids go down when you were like young. You never have that vertical motion. That's why f of y is always equal to 0, or the sum of all those forces is equal to 0. Because in this problem and in the previous problem that we did, our f of y motion is always 0. Okay. Oh yeah, sure. I can explain why tension cancel out. Are you going to annotate for me, Mo? I was about to explain why tension cancels out, but then people have been asking questions.
Yeah, if you want to answer Alap's question, I can ask my question next.
Sure. So Alap's question, I'm just writing all the actual real forces down. And if you look at the tensions, look what the arrows are doing. They're equal and opposite to each other. So they're going to cancel out when you take it as a whole. Does that make sense for Alap? Cool. Go ahead, ask your question, Mo.
Sure. So my question is, Is it okay if we skip that triangle step and just do this instead? I mean, this is the way I solved it. This is the y, x, and that's theta right there.
Yeah,
So-
because isn't an ulterior angle to this? Here's your two parallel lines. I'm going to draw it in green so you guys can see. This is green. This is green. Here's your transversal. That's why you're going to get that angle being theta. But yeah, keep on going.
Sure, yeah. So yeah, and that's the line below horizontal. Sorry, I switched colors right there. And then the force would be theta degrees below the horizontal, so sine theta and 2 mg sine theta. That's the way I made sense of it. This triangle, the other triangle step for me is more steps. To me, I just think of it easier this way. So is that accept? Do I make mistakes if I do it this way, or is it perfectly reasonable way to solve these kind of problems?
Why would you? Oh, you're taking mg to be perfectly down, and then you're going to be taking the sine component of that because it's on the opposite side of this system.
Yeah. So if I'm doing it here, so
Yeah.
So, and then this is theta, and that's 2 mg sine theta because of that angle right there. I don't know if anyone else did it this way, but that's the way I usually solve these kind of problems.
Yeah, it looks like it could work. I personally I do it this way. I always write it out like this. I can group this as a whole, and then I just simply do my 2 mg sine of theta minus mg is equal to 0, right? I ignore all of the thing, and that's equal to actually 3m a, but a is equal to 0. So I simplified even further, and I do this, so I don't have to worry about all that other stuff. But this goes into you understanding that you need to be able to break this weight vector into components correctly.
Yep.
So then you get rid of all your m's, and then you can bring the g over to the other side, divide by 2, g, then you're going to get sine is equal to 1/2. In that case, it's when it's 30 degrees. Okay. 3 MA. So Vinay asked, why does right side equal to 2 MA? It's actually 3 MA. Are you talking about up here?
Yes.
Oh, what mass are we using? What's the total mass?
Oh, 2m. Yeah.
Yeah, there you go. Right?
Okay.
So it's whatever the mass is. In this case, I made it 2m instead of just m. Right? And over here, this was just m, so then that's just MA. Do you see? But here, you're taking it as a group as a whole. That's why it's 3m. Does that make sense?
Yes.
Cool. So last week we did helpful right triangles, right, Michaela? 60, 30, 90, right? It's easy as 1, 2, 3. So when is sine equal to 1/2?
Oh, I get that part. I was just meaning like how you broke down the like the force equations for the 2m block and then the m block differently and then put them together. Sorry.
Oh, okay. So look, for the y component here, I did up minus down. And then
Okay.
the other one, I did left minus right. It's the same thing as what I did here in this one. Up minus down, right minus left, or left minus right.
Okay.
Does that make sense? That's how I got it. Remember, this is my new y, and this is down from that. So I did up minus down.
Yes. Okay.
I redrew that right here. Do you see?
Yeah.
And then how did I do it? I did up minus down, up minus down, and then I did right minus left, which is right minus left.
Okay. Thank you.
Now, if you go back to the other picture, you'll see the same thing, right? Normal force is pointing up. The opposite to that is 2mg cosine theta.
Mm-hmm.
Normal force minus 2mg cosine theta. 2mg sine theta is going down on the incline. Tension is going up on the incline. So I did that minus the tension.
Okay. That makes sense. Thank you.
Yep. Cool. No, this is good. Usually when people have questions, other people have questions. And thanks, Brooke, for confirming that. Yeah, you choose, like, to be honest, you get to choose what's positive and what's negative. There's just make sure that it's consistent. So notice that I kept the consistency here. I made that my 2mg positive, which also made this tension positive. So this was positive and this was positive here. Do you see? This was negative, which is what this is, and this mg was negative. So I kept that consistent with each other. Do you see that? So going to the left, I made positive. Going to the right, I made negative. And I kept it consistent. So when you're not consistent, then you end up with a negative sign where you're not supposed to have. You're supposed to have it. Okay. Good. Let's deal with this problem where you have a frictionless surface of an object of one mass attached to a string and pulley again. On the other end, there's an object of a second mass. I want to find the acceleration of my system as it falls. Answer choices are as follows. Acceleration is equal to m2 squared all over m1 times m1 minus m2 g. G's in the top, sorry. B. Acceleration is equal to m2 squared all over m1 plus m2 g. C. Acceleration is equal to m1 all over m1 plus m2 g. D. Acceleration is equal to m2 all over m1 plus m2 g. So find me the correct acceleration. So in this case, this type of problem is what we call dynamics. The objects are now in motion. Before, the objects were staying still, and that class of problem was called statics. It sounds scary. It's literally the only difference is before MA was equal to 0, now MA is not equal to 0. You have to solve for the A. Okay.
You said frictionless, right?
Yes, ice is considered frictionless. In B, M1 plus M2, correct. Rewrite that. Same thing for D. The denominator is M1 plus M2 for B, C, and D. The only thing that changes are the numerators for B, C, and D. They're all multiplied to gravity still. For these type of problems, I used to love them when they came to the MCAT. Because one, I would know that a lot of other students that are taking the tests would spend lots of time, and I can do these types of problems. It takes me about 10 seconds. So I still want you guys to do the force problem recipe to show that, look, if we go through, do the force problem recipe, we're going to get it correct. But in terms of interest of saving time, I'm going to show you some test taking tips so we can do these questions a lot easier. Okay, I think that's enough time to do this. So let's take a look. So I'm not going to do the typical force problem because I'm trying to teach you something new. I'm going to take a look at what we call the limiting cases. This is an example of taking what we call the limiting cases. So the first case that I'm going to take is when m1 goes to 0, or it's non-existent. So if m1 goes to 0, what's acceleration in my system going to be? Imagine it goes away. Yeah, acceleration would just be gravity, right? The force would become m2g. Yep, that's correct. So wherever we see m1, we plug in 0, we expect to get g. We plug in 0 here. Something to multiply to 0 is 0. Something divided by 0 is undefined. That goes away. m1 is 0, so you get m2 squared over m2 and then multiplied by g. So that's a force, not even an acceleration. So that goes away. We plug in 0 for m1, we get 0 over m2. So 0 times g is just 0. That's not gravity. We plug in 0 for m1, we get m2 over m2 becomes g. We're done. Pretty easy, right? 10-second problem. I just chose the limiting cases. So you can either choose m1 to be 0 or m2 to be 0. Why not b again? Because what happens when you plug it in b? So a is equal to m2 squared all over 0 plus m2 times g. So this becomes m2g. That's a force, right? Mass times gravity. That's not an acceleration, Michaela. So that's why it's gone. You didn't keep your directions consistent, Melody. Well, I'll show you how you made that mistake. Sure, I'll go over B and C again. So I just went over B. C, acceleration. We plug in 0 for M1. That becomes 0 over 0 plus M2G. That makes acceleration 0, not gravity. So that's why it's wrong. Okay, I'm going over the shortcut. My shortcut is I plug in 0 and see if it comes out with acceleration of gravity. Okay? For number 1, we have acceleration of m2 squared all over 0 times gravity. Acceleration is something divided by 0, so that's undefined. Is that g? Yes or no? Okay, that's why it's gone. That was A. B, acceleration is equal to m2 squared all over 0 plus m2 times g. That's m2g. Is that even an acceleration? No, that's a force. That's why that's gone. C, acceleration is equal to 0 over 0 plus m2 times gravity. This makes acceleration 0. Is that g? No. And D, acceleration is equal to m2 all over 0 plus m2 times g. Is that gravity? Yes, it is. We're done. Typically, I just do this mentally in my head, where I plug in 0 and I see what I get as an answer. Does that make sense? Can I erase the logic of this? Because I'm still going to work it out, because there's tons of problems. Any problems that you have in motion, you should be expecting a certain motion that you get out of it, right? And if you eliminate certain variables, then your acceleration will be just certain values. So anytime there's an object with a type of motion type problem, Jagger, you can basically do this limiting cases. So last week when we talked about your velocity as a function of displacement, right? You could have done it there, right? That is correct, Jonathan. Because we know that if M1 is gone, then it's just a falling object. Yeah, it's super useful. I always love these type of problems because, hey, look, a problem that took you guys like 2 minutes to 3 minutes, I'm doing in 10 seconds. That means I have 2 to 3 minutes for another problem that requires a lot of work. Yeah, you can choose M2 to be 0 too, right? So if we choose M2 to be 0, for the other case, acceleration should be 0, right? Because M1 in this case isn't adding to the system, Tiffany. It's not part of like the mass. There's no M1G that's pulling down. So before, when we did our kinematics, everything, all those objects that we had were just the mass of that object that's floating in space. But if we started connecting those masses to other masses that don't have a component that's also pulling down, then you can't just cancel out their masses. You could have done it with any of those like multiple type problems that they have with like variables in them. You can do this limiting cases. Okay, Sophie, if this mass is no longer here, what's going to happen with M1? Exactly. So what's the acceleration of nothing? Nothing, 0. Right? Erase it, right? Because that's what M2 being 0 means, right? It's no longer there. We don't have to worry about it. I'm just going to draw it back for the problem. Okay? So I'm still going to work it out. Don't worry, I haven't forgotten about you, Melody. Yes, that's why I chose case 1. 10 seconds. Fastest method possible, right? Yes, you're still left with stuff. Yes, when you erased it, it clicked, right? Because in case 1, what happened? In case 1, M1 goes away. Ta-da! Correct. So yes, you're right, Melody. In case 2, where M2 is equal to 0, acceleration is equal to 0, both A and B are still valid. The only one we end up canceling out is C. D is still valid as well. A, B, and D are still valid. But in case 1, it cancels out all A, B, and C, and leaving only D valid. Okay, so now let's go and do why Melody got a negative, because that's also a common mistake. And this is, that is correct. You should try both. I'll have to answer that question later, okay, Tiffany? Because I still have to get to torque still. Yes, you should always try both cases. One of them will help limit better than the other. But between the two of them, you should be able to cancel out every invalid choice. So let's look at why Melody missed it. So here, I'm still in erase mode. Here we have tension, here we have tension, and here we have M2G, right? So for M1, we have tension, and that's equal to M1A. For M2, notice that this is positive, so going down this way is positive. So you should make this M2G positive minus T is equal to M2A. I bet my bottom dollar that Melody made tension positive. Correct? For the M2 mass. Yes. So this is where the inconsistency of not choosing a direction and keeping it the same value is going to make your answer have that negative value. Because you didn't keep consistent. So we made this tension the positive direction. And so therefore going down along this rope, M2G is the positive direction. So we have to keep that consistent with each other. Notice I chose going down where acceleration was positive because this, and this are all positive values, right? There's no negative anywhere. Okay. So then I just substitute that in here. We get M2G minus M1A is equal to M2A. Bring this to the other side. M2G is equal to M1A plus M2A, factor out the A and divide, and then that gets us to our answer. Good grief, I accidentally deleted it, but it's fine. So we're here, M2G is equal to M1A plus M2A, factor it out, so M1 plus M2A, M2G, so A is equal to M2G divided by M1 plus M2. Apologies, I deleted that slide. Fat fingers. I can break it down in X and Y. What's the point though?
Sorry, can I just unmute?
Yeah, go
so
for
I
it.
can. Okay, like why wouldn't the up and down of like I did the M1 up and down as like positive Y and negative Y. So why wouldn't that like transfer over to M2?
So here's the rope, right? So if you're going to make that case where this is M2 and this was M2G, and you made T minus M2G here, right? And you made this positive. So this one going this way has to be negative. So you should have wrote negative T is equal to negative M1A. Negative M2A. Because all the directions that you're going downwards, this has to be a negative direction, right?
Yeah.
So if you do that, you need to be consistent. This is what I mean when you need to be consistent with the notation direction. This is negative. This is negative. That acceleration is negative.
Got it. Thank you.
Yeah, because you didn't do that, that's going to give you an answer where you don't have that correct. Make sense? Cool. That's what I meant when I say that you have to be consistent with your directions. Okay, so that's your statics and dynamics for forces. Now we're going to move on and talk about work and energy. Okay, so let's define work and energy. Work is simply changing an object's, oh my god, can't spell. Mechanical energy. So when we talk about mechanical energy, we're talking about kinetic and potential. Okay. So we define work as simply the parallel force times displacement. So let's take a look at it. The units for work is a Newton times meter, otherwise known as a joule, denoted as capital J for short. Okay. New unit. So what do you mean by parallel force, Khoi? So this is the equation. So you should remember parallel force times displacement gives me work. So if I have a displacement direction that's in this direction and we have a force vector that's in this direction, we want the parallel component of that force or the projection of that vector onto the displacement direction given some angle. So then that's going to be F cosine of that angle. So the parallel force times that displacement, right? We're ignoring the perpendicular component right here because that's not going to help us move in that horizontal direction of the displacement vector. Does that make sense? So we're taking what we talked about with forces just now and breaking them into components and applying them to work, which is simply taking that force or the parallel component of force multiplied to displacement. So work is simply force cosine of the angle times d, or written as FD cosine of the angle is your work. The units for work is a joule. Now, if that angle is less than 90 degrees, then we're going to have positive change in energy. If that angle is equal to 90 degrees, then we have no change in energy or no work being done. And if that angle is greater than 90 degrees, we're going to have that change in energy being negative, or negative work is being done on the object. Or work is being taken, or energy is being taken out due to work from that object. The perfect example of this, parallel, it's just two parallel lines. That's my symbol for parallel, right? Because this is parallel, this is perpendicular. Sorry. I said parallel force, I just didn't denote that that's what those two parallel lines mean. So how do we get negative work? Right? So if you think about it, friction, so displacement direction is usually one way, frictional force is usually the opposite way, right? So if we use our equation, work is force times displacement times the cosine of the angle in between. What's this angle? Between friction and displacement? 180. So what's cosine of 180? Look at your helpful right triangles, Jonathan. And your unit circle. I expect you guys to know this. Correct, Zoe. That's -1. So that's how you get negative work. Whenever that force or some component of that force is in the opposite direction to your displacement, that force is going to be taking away energy from your object. Does that make sense? Or how we get negative work? So both of these equations are equations for work, parallel force times displacement, or FD cosine of the angle in between. Okay? So let's take a look at a problem using what we've already done, except we're going one step further. So we have some object of mass m here. That mass is 5 kilos. Mu of kinetic friction is 0.4. The displacement that it travels is 10 meters. I even tell you that the angle of this incline is 30 degrees. So I want to know, what is the work done by normal force? What is the work done by friction? And what is the work done by the weight of this object? So all we're doing now is taking those forces, multiplying it by a displacement, and multiplying it by the cosine of the angle in between those two forces. The two vectors, the displacement vector and the force vector. So, work done by normal force, work done by friction, work done by the weight. Mu k is equal to 0.4. So coefficient of kinetic friction is equal to 0.4. Sorry, Leandro. I have to switch back and forth to check the text box. It's not parallel on the iOS. So you should be able to draw your normal forces. Remember, perpendicular to our resting surface. Weight is always straight down still. Work done by normal force. Amanda. Work done by friction, work done by the weight. So these are all those forces that we talked about in the first half of class, your friction, your normal force, your weight. So now we're going to try to find the work that's done by each one of them. So what's the work done by normal force? This should be the easy one out of the three. Correct. So we have normal force times displacement times the cosine of 90, right? Displacement's parallel, normal force is perpendicular to the incline. So what's cosine of 90? 0. So what do we notice? Forces that act perpendicular to our motion of direction don't contribute any work to that direction. What about friction? How do we define work? Work is the angle in between the force vector and the displacement vector. Sorry, I had a student ask, why is it cosine of 90, not 30? So what's the force? What's the angle between the force, in this case, your normal force, and your displacement vector? What's that angle? What's this angle right here? Is that 30? Nope. That's 90 degrees. Does that answer your question for the student that asked why cosine of 90, not cosine of 30? Good. Careful, this is force of friction. So it's negative, there's a negative. Right? And then there's the frictional force, which is coefficient of friction times normal force, which is mg cosine of 30 times your displacement, right? This was force of friction times d, right? And this is the negative from that cosine of 180, right? We did that in this problem right here. This is the work done by friction. Negative times frictional force times displacement. All I'm doing is substituting it back here. Negative frictional force times displacement.
So why is it cosine 30 instead of 180?
Because this is normal force. This is this vector right here, right? This is from frictional force. This is the cosine of 180 right here. That's what negative 1 is. And yes, frictional work is always negative. Did I answer that question?
Yeah, but then I'm confused. If if friction is at an angle of 30 degrees, then why is the normal force just 90? Why isn't it not? Why isn't it 90 plus or minus 30?
Okay, so let's erase it. Let me write down negative, and then I'm going to write down cosine of 180 if that makes you more comfortable. And I just made that -1, okay?
Yeah, that makes sense. I'm just asking about that 30 over here.
How did we find friction before? All the way back here. Coefficient of friction times normal force. How did we find normal force? Normal force minus mg cosine of theta.
Oh god, I think that's what I was missing.
And then we substituted that in. I just skipped that step because we for the first half of class.
So in the problem, we're actually solving for the mg. Oh no, it's cosine, not sine.
This is mg cosine, right? Because this is theta, this is the adjacent side.
But aren't we looking for the friction, which the vector is pointing uphill?
Yeah, that's what this 180 was. That's what the -1 is taking into account.
Because if you complete the triangle from the arrow that's almost off the page, and then complete that down to the mg, yeah. And then couldn't we put an arrow tip pointing to the arrow tip on other side? Oh no, yeah, right.
Trying to refer to, and when you say arrow tip to arrow tip, that's not descriptive. Which arrow to which arrow tip?
It looks well. So that line that you just drew is perpendicular to the line of friction, and
this line that I drew, or this line? This line that I drew is to find normal force.
Right. So if we're looking,
and so what's the equation for friction?
Try annotating.
Let's go back. What's the equation for friction? Coefficient of friction times normal force. So, how do we get normal force? Normal force is equal and opposite to mg cosine theta. So cosine of theta in this case was 30.
yeah, it just doesn't seem. I see what you're saying, but it doesn't seem intuitive because we have that other. It makes me think we should be using mg sine of theta to get the side of the triangle opposite theta, and then flip the sine.
Okay, so this is normal force, correct? Can you agree with me on that, or you're still?
No, that I agree with you. Yeah, I was just saying I agree with you that makes sense. But intuitively, when you look at the vectors on the drawing, it looks like
No, we're looking at this equation right here. Do you see?
Mhm.
That's K times normal force. How do we get normal force though? By doing the y component of this force vector.
the y component of the normal force vector.
Yes, the y component here. This minus this.
And there's no x component.
Yeah, this is the sum of the forces in the y, right? Normal minus mg cosine of 30. We did that right here. We did that right here. So why is that hard to see right here?
Yeah, well, I just joined the lecture, so sorry I didn't see those others, but I think what I was mixing it up with was looking for the vector in the x direction. So if I were
the vector is this vector, right? That we're talking about, the friction vector.
right.
And then that's force times displacement. So we go back to work. The definition of work is force times displacement times the cosine of the angle in between. So force times displacement times the cosine of the angle in between. That angle being 180 degrees. Vinay, you're still confused?
No, I'm catching along.
Okay. Does that make sense where I got it from? I just skipped that step because in the interest of saving time and not repeating summation of forces again, I didn't go over it again. Okay, so let's erase this. So now we can just substitute in the numbers. So what do you get? I think Zoe did it. And she ended up getting negative 100 root 3, which is approximately negative 173 joules. By the way, you guys should know your approximation. Root 3 is 1.73 and root 2 is 1.41. This is when you do your sine and cosines of 30, 60, and 45. When you get root 2 over 2, when you get root 3 over 2, approximately. And then the work done by the weight vector, you have weight times the displacement vector, and then I just need this angle. So mg times d times the cosine of the angle in between. So what's this angle? This is 90, this is 30. That has to be look at this triangle.
60.
Correct. 90, 30, 60. What's cosine of 60? Look at the helpful right triangles from last week. Yep. Times a half. So that's going to be equal to 250 joules. Does everyone follow along? I want to make sure everyone understands. Okay. So that's work. Now let's take a look at energy. So with energy, energy gives an object the ability to do work. There are two types of energy. Actually, there's three types of energy. The first is kinetic energy. This is energy of motion. There are two types of kinetic energy. The first is your translational kinetic. This is the one everyone learned. And that's equal to what? You guys know kinetic energy to be what? 1/2 mv squared. Then there's rotational kinetic. It's 1/2 times the moment of inertia times angular velocity squared. So translational kinetic, rotational kinetic. Okay. both are energies of motion. So whether an object is moving it at some velocity or rotating it at some angular velocity, you're going to have kinetic energy. The second type of energy is energy of position. So potential energy is energy of position. The first type of potential energy is gravitational potential. First type is when we're close to Earth, which is basically most of the types that you're going to see for your MCAT. That's equal to mgh. And the second type is when we're far from Earth. Gravitational potential energy is the universal gravitational constant, mass of one times mass of the other, divided by the distance between them. And it's negative. So when it comes to large planetary body type things, we're going to use the second equation. We're going to use the first equation when we're close to Earth. So the reason that when we take an object and get it to drop, it's, if you think of an object with some mass that's dropping to the ground, and you think about this as the Earth, right? These two objects are coming closer together. So when that happens, this is considered negative mgh, right? Same thing as this is considered negative for those two masses to come together when we're talking about planetary objects. It says equal to negative g, mass of one times mass of the other, divided by r, where g is the universal gravitational constant, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Universal gravitational constant. U sub g. So this U sub g is another symbol for potential energy. Newton meter squared per kilogram squared. There. Sorry, I wrote it. Should have been more clear. Thanks, Lexi, for clarifying. Did I answer your question, Masha? Okay, awesome. Sorry about that. I was trying to rush. That's why I'm like trying to get you guys out on time. The other type of potential energy is elastic potential energy. And with elastic potential energy, I need to go over Hooke's law. Hooke's law has to deal with the spring. So here's a wall, here's a spring with a mass attached to it. So if it was staying at rest here when this was x is equal to 0, we've stretched it a positive x direction. Your spring force is going to be acting in the opposite of that. The spring force on a spring, is equal to negative times the spring constant k times x. K is what we call a spring constant. It is a constant that will be given to you. It's based on the properties of the spring, the type of metal, the number of loops, and the density of that spring. and x is displacement from equilibrium. X equals 0 is equilibrium. So wherever we move it, if we compress the spring a negative x displacement, the force is going to be acting in the opposite direction. That's what this negative is. I call that my restoring component. Okay. So that's your spring force. So what elastic potential energy takes into account is the average spring force over a period of time. So if this was your spring force as a function of displacement, it's always going to be some positive linear. We're going to take the average of that. So the average force is going to be 1/2 kx, right, in your system. And then if we multiply that by displacement, so elastic potential energy, PE elastic, is simply 1/2 kx multiplied to a displacement, right? So here's your average force multiplied to a displacement. That gives you work. That work leads to a change in potential energy of my system. So elastic potential energy is 1/2 kx squared. Okay? So this is the equation for elastic potential energy. The third type of energy that you guys need to know, that is, so the cool thing about, let's go back one slide. The cool thing about kinetic and potential energies, both KE and PE are reversible. So what does it mean to be reversible? That means that I can do work on my system and get back that energy. It says average force, F average. Sorry. That's what this is. Average, I'm just carrying it up here. So F average times displacement gives me my elastic potential energy. Let's write it neatly. Okay. So both KE and PE are reversible energies. That means we can do work on the system and we can get our energy back. Okay. The third type of energy that we're going to discuss is not reversible. This is your heat energy. In chemistry, when we talk about heat energy, this is the energy given off from bonds being broken, bonds being formed. This is the energy that ends up going and becoming entropy in the universe, right? So heat energy, Q, is equal to M CP delta T. Units are still in joules. Mass is in kilograms. Heat capacity at constant pressure, joules, is kilograms Kelvin. And temperature is always in the units of Kelvin. And heat is in the unit of joules. Okay, so kilograms will cancel out, kelvins will cancel out, leaving you with joules. Remember that Kelvin is simply 273.16 Kelvin plus degrees Celsius. Yep, everyone always likes to remember that it's MCAT. And if they ever try to mess with you and may give you something in Fahrenheit, it's 9/5 degrees Celsius plus 32 is degrees Fahrenheit. P, the subscript of C is P. So Cp is heat capacity. At constant pressure. The reason we say constant pressure, because here on the surface of the Earth, we're always at 1 atmosphere. You also will do, if you do thermo, when we talk about thermo, you're going to have heat capacity at constant volume. Okay. So that's what subscript P stands for and subscript V stands for. And if you actually take Cp over Cv, that's equal to your universal gas constant, R. Okay, but we'll get into that when we get to thermo. But right now, all you guys need to remember is that heat energy. This is a non-reversible. Oh my God, I need to stop writing so small. Energy. I can't, once I break a chemical bond, I can't get the energy stored in that chemical bond back, right? So if you think about it, this is what we use, Q is equal to MCAT or MCP delta T, to deal with calorimetry, right? When we were doing about exothermic and endothermic type of reactions. So when we talk about heat energy as a whole, we're talking about energy that we cannot change back or get back easily. R is the universal gas constant from chemistry. Right, 0.0821. So kPa, liters per mole Kelvin. But we'll get more into that when we talk about thermodynamics and gases. But this is where that energy is coming from. And we'll get more into that when we talk about that specific lecture on thermo. Okay, thermochemistry, thermodynamics. So this is the third type of energy. So I'm going to erase this board since it's mostly erased already. So let's take a look at what we call the work energy theorem, where you can combine energy and work and interchange them with each other. So today we learned about kinetic energy, which is 1/2 mv squared. In week 1, we learned that final velocity squared is equal to initial velocity squared plus 2 times acceleration times the change in displacement. And earlier today, we learned that F is equal to ma for Newton's second law. So we substitute in for A. So we get force times the change in displacement. What is that? We learned that today. What's force times change in displacement? Work. Very good. So if we move everything to the other side and keep that on one side, let's see what we get. V final squared minus V initial squared multiplied by the mass divided by 2 is equal to force times the change in displacement. So we see work on the right-hand side, and on the left-hand side, we have what? The change in kinetic energy. So work is equivalent to the change in kinetic energy or the change in potential energy of our system. So they will ask you questions about work and give you kinetic energy terms and vice versa. They'll ask you kinetic energy questions and give you forces and displacement for work. So be able to be flexible and use them interchangeably with each other. Okay. last thing that we need to discuss, and I'll give you one problem and then we'll be done. Let's get rid of this. Newton's laws, we don't need these in terms of going back. So let's look at the last thing we need to look at. It's just the law of conservation of energy. Law of conservation of energy simply states this. In the absence of friction, the total mechanical energy of a system remains constant. So it's basically saying that if energy is consistent of only kinetic plus potential, i.e. mechanical energy, and there's no friction, then the change in energy of my system is equal to 0. And in doing so, we can say that initial kinetic plus initial potential is equal to final kinetic plus final potential. And so this is without friction. Now, if you had friction, it'll still be the same thing, initial kinetic plus initial potential. But at the end, after getting the potential and the kinetic energy, you'll also have the work done by friction. This is with friction. So you've done enough of these type of problems from your kinematics so that when we look at it again, let's get rid of my force problem recipe. We're gonna clear that. And so you get this type of problem, right? So you have an object at a height of 40 meters traveling at a velocity of 10 meters per second. And the mass of that object is 5 kilograms. Find the final velocity of that object just before it hits the ground. So at the beginning, you ask yourself, do I have position? Do we at the beginning? Position is what? Height, displacement. Do we have that? Yep. Is that the answer, Mo?
Yes, 10 meters above the ground, right?
It's 40 meters above the ground.
Oh.
But yes. Sorry if it looked like a 10. Yes, that's correct, Renee. So, but I care about setting it up more than I care about solving for an answer. So, do we have position? Yes, we have potential energy. Do we have motion? Yes, we have kinetic energy. At the end, we have kinetic energy. Right? There's no position because you're at 0, because it's just before it hits the ground. So we have mgh plus 1/2 mv initial squared is equal to 1/2 mv final squared, right? Cancel out all the m's, multiply everything by 2. 2gh plus v initial squared is equal to v final squared. That equation look familiar to you? Yes, no, maybe so.
Yeah, it's one of those uniform accelerated motion equation.
Yeah, that's where they came from, right? Conservation of energy. So, it does normally, Tiffany, for that answer to your question, but when we're doing it with forces, they don't cancel out completely because there's certain dead weight that's like hanging on. So, V final in this case is just the square root of 2 times 10 times 40 plus 10 squared, right? So that's 800 plus 100 gives you 900. Square root of 900 is 30 meters, like Vinay said. But along the way, we saw that, hey, this equation comes back into play and takes care of itself, right? And where it came from, using conservation of energy. So I remember learning this after doing all those kinematics, breaking vectors into components, and doing all of that stuff with forces. And when they taught us about work and energy, we only care about what's the beginning and what's the end, or where we wanted to look at. It becomes like super easy. The reason being, this section, I think everyone did really well with work and energy, and they did horribly with forces and kinematics, is that work and energy are all scalar terms, as opposed to kinematics and forces, which are all vector terms, which is why we needed to decompose them, break them into vectors and different components, and then recombine them. But with work and energy, you're just simply plugging into the equation. Potential energy is mgh, kinetic energy is 1/2 mv squared. And your final velocity is just simply your solving of that work and energy type system. Okay. All right. With that said, if you guys have questions, I'll be here until at the latest 5. If not, I will see you guys on Wednesday. I will be posting office hours, or have Josh post office hours of my office hours this week. I'll be starting them. I'll try to start them tomorrow. On Tuesday, I'll try to do them from 1 to 2 before class starts. So, but and then Thursday as well. So if you have any questions, feel free to ask. Otherwise, I will see you guys on Wednesday.
I have a question.
Thanks, Ayla. Sure.
So could we, I know you went through it a couple times, so could we go back to like drawing vectors just so I can be clear on it? Because for some reason it's just not clicking.
Sure. Which one did you want to go back to?
We can go back to the first one that you did.
On forces?
Yes, I think so.
Okay. Sure. This one?
Yes.
Okay. So I did my force problem recipe. So let's do it on a blank slate. Let's go back to that last slide on what I did work and energy on. This one. Let's just clear this. So we had the problem of the inclined plane, right?
Mm-hmm.
And we have an object at rest on that inclined plane of mass m, and there's some angle here that we don't know, right? Okay, let's go in order. Okay, thank you for those who are asking questions. And no, I didn't see your email, Vinay. Was it just today, or was it like way earlier? Vinay? Hello, hello? I guess he left. Okay. All right. I will answer yours right now, Michaela, because you are here. And
Well.
answer it if you're not going to stay. Okay, so I'll get to yours after, okay, Tiffany? Let me see. I'll go in order. Yeah, you're next, Tiffany. Okay, so we're looking at vectors, right? So let's draw our vectors. What are the vectors acting on this object?
You have the normal force going perpendicular, so straight up.
Not straight up. Perpendicular is this direction.
Yeah, that's part of my problem. Okay.
Yeah. Perpendicular to what? The resting surface.
Okay.
So if you have an object on a wall, your normal force is perpendicular to that wall.
Okay. So
Does
it's perpendicular to the surface.
It's perpendicular to the resting surface. I believe
Okay.
I wrote that right here. And then
Yeah.
Okay.
Okay.
So it's perpendicular to our resting surface. Let's erase this. Okay. What
Mhm.
else?
And then we have the friction force pulling backwards on it.
Mm-hmm.
And then we have gravity pulling it forward.
Gravity pulling down. Gravity only pulls down. It never pulls forward.
Okay. Or
When we look at the components of gravity, yes, there's a component of gravity that's pulling it forward, but gravity itself acts straight down.
okay, and so that's like the weight.
Mm-hmm. Weight is
Okay.
always straight down. Okay.
Okay.
And so the force of friction is some coefficient of friction times normal force, right? That's the equation that was given for friction.
Mm-hmm.
Now we need to break our components, mg, into a y and an x component, right? So we're going to choose this to be our y, and this is to be our x. Okay. So here's I'm going to choose it to be, I'm going to draw the other triangle.
Yeah.
So it's easier. So here's my x, and then I'm going to choose a component this is my y.
Okay. So X.
So I can
and
draw
Y.
the same thing here, and I'm going to draw the same thing here. Sorry, I didn't connect it all. I just didn't leave enough room. Does that make sense?
Yes.
And then this angle is what? 90 minus theta, correct?
Mm-hmm.
This is 90, this is 90 minus theta.
Yeah.
So then this angle down here has to be theta, right?
Yeah.
Here.
Oh wait. So that angle of the triangle. Okay.
Because this is also 90-degree angle, right?
Yeah. Okay,
So-
that makes sense.
So then this is the opposite side. The blue is the opposite side
Of which angle?
of theta,
Yeah. Okay.
right? So that's why it's mg sine of the angle.
Mm-hmm.
And the green is the adjacent side
So it's mg cosine.
the angle.
Okay. And then on the other side.
On the other triangle, this is mg cosine. And this is mg sine. Do you see how they all point in the same direction for the blues and the greens?
Yes.
Whatever you use.
Which theta did you use? The one at the top by the green?
Yes.
Okay.
This angle here is opposite. This side is adjacent, right? So that side is the opposite side. Hence why it's sine.
Opposite. So, yeah, okay.
We're good.
Yes.
So now I'm just doing up minus down, up along the y direction, minus down.
Mm-hmm.
So what vector is pointing up along this y direction?
The normal force.
Mm-hmm. What's pointing down?
The like the weight
No.
or
Along the y direction.
mg cosine theta.
Yes.
Okay.
And that's equal to ma in the y direction, right?
Mm-hmm.
Now we do the sum of the forces in the x direction. So what's pointing down and what's pointing up?
So it would be in the x direction, it would be mg sine theta. Or
Mhm.
wait, pointing down and pointing up, you said?
Yeah, right minus left, right?
Oh, okay, yeah. So going right would be the mg sine of theta minus the mg cosine theta. Oh, no, the friction force.
Yeah, which is mu s times normal force,
Yeah.
which is mass times set equal to ma, right?
Mm-hmm.
Newton's second law. So we have two equations. We don't know normal force, we don't know theta. And we have two unknowns. Can you solve that system of linear equations?
Yes.
How would you go about solving that?
Moving the mg cosine theta to the other side within the vector for y, and then you would know what n equals, and then you would plug it into the bottom equation.
Yeah, so that method is called substitution, right? Remember when we did this for algebra 2? It
Yeah.
was either elimination or substitution. So we're using substitution. Good.
And y is acceleration 0.
And the problem, I had it before it begins to slide.
Okay.
So
it's resting basically.
the rest.
Okay.
Then we substitute it in here. That's how you get mg sine theta is equal to mu s mg cosine of theta. Cancel it out. Divide both sides by cosine. Sine over cosine is what?
Tangent.
Tangent is equal to mu s. So theta is equal to the arctangent or inverse tangent of mu s. So that's what we're solving for, right?
Yes.
But the steps, all of this is just algebra, right? You could just solve for any darn variable that you didn't know.
Yeah.
But the setup is you drawing these vectors correctly and going up minus down, right minus left.
Yeah.
That's literally every problem that we did, right, Michaela?
Yeah, exactly. I don't know why it's just so hard for me to see like which way to put the angles and like which way to draw the sines and the cosines, if that makes sense.
Mm-hmm.
But yeah, I'll keep doing practice problems. Thank you.
Yep. All right, Tiffany, let's go. What question did you have? What was your first question? It was a while ago.
Hi, can you hear me?
Yeah. Yeah, I can hear you.
Yeah, so I was just let me pull up the question. Yeah, so when we talked about kinematics, we said that the acceleration and velocity is independent of the mass, but now we're looking at these objects. We saw that if we go back to I think it's the pulley question, we have an incline, we have M1, M2. I think it's
This one, right?
this one, yeah. So when M2 gets heavier, the object falls down faster because MA equals pretty much MG.
Yeah.
Yeah. I just wondering what's the difference. How come now
Oh,
mass matters before mass?
okay. So before, like when we're talking about objects in space, it's just the mass by itself, right? So the only force acting on it was its own weight, correct? And so when we do it, set it equal to ma, the masses cancel out, which is true what you said.
Do you mind writing that down? I have trouble like seeing it. Sorry. And like
Sure.
canceling out part.
Yeah. So if you think about it, like in space, right? When we talked about those projectiles that are going in a parabolic path, right? What's the only force acting on it?
Gravity.
Mg, right?
Yeah.
Gravitational force. Why is it not writing? Sorry. There it is. Sorry. Oh, I know why. My pencil is about to die. Sorry. Give me like 20 seconds and it'll charge again.
No worries.
Enough.
No worries.
8 minutes in use. Okay. That's why I wasn't writing because it's about to die. So at any given point, right? The force on it was mg. The force on it was mg,
Right.
right? And so if the only force on it is mg, when we do sum of the forces and set it equal to ma, the only acceleration it had was gravity. correct?
Right.
Except now, this object here has a mass in tow, right? Where it has no net force of gravity acting on it, right?
I think I get it now. I think
Now it's just like, okay, if you were falling, but you also had to drag someone else's backpack with you, right? That wasn't having a net force yet. Because here, if you think about it, oh my God, I wrote it. Normal force is canceling out the weight of this object right here because it's at rest on it, right? Newton's third law. So since this has no net force on it, the only net force is coming from this. That's why when I did my summary one, the M1 minus connected to M2, and this is the only real force acting on that object, I think of this as a whole, then it's just simply M2 is equal to the total mass, M1 plus M2 times A. So now your acceleration isn't canceling out because there's part of this weight that isn't just flying in space, like these problems above. Does that make sense?
I think I'm gonna sit on it and see if I understand it. If I don't, I'll ask you again.
Yeah, it's because this mass of M1 is just being dead weight that's dragged along, where there's no net force of it that's pulling down due to gravity because it's being canceled out right now because it's at rest.
I guess I think I'm thinking too much, but for the sake of like the MCAT, what should I be doing like when it comes to like acceleration?
Well, if you think about it, all of these things are tools that you're going to be using to deal with magnetic forces, electrostatic forces, fluids, force due to pressure within the body. Because, like I said, most of book one is going to be practice to apply to book two. So that's why I want to teach you guys the basics for kinematics, forces, work and energy, torques, so that then we can apply it to your fluidics, your torques, which is any point in your body where it pivots and rotates, and then your electrostatics and electromagnetism and circuits. Circuits and fluids are basically the same, right? Electric circuits. So instead of calling it potential, we're talking about pressure difference, right? Or gradient. Instead of calling it ions, we're calling it mass or water molecules, right? Instead of calling it current, we call it current flow, right? Electric current versus current flow. They're very analogous to each other. So, but you need to understand why it's doing that, because there's forces in play that are pushing these molecules to move. So you need to understand this well enough so that you can apply it to those macroscopic properties of fluid motion, electrostatics, electromagnetism, and your electric circuits, and in a sense, light as well.
Okay, got it. I'll make sure and try to understand this, and if I don't, I'll ask you again.
Yeah, that's what office hours are for. Okay, so feel free to ask me that in the office hours.
Thank you. Thank you so much
Yep.
for your help.
Yes.
Have
Thanks,
a
Tiff.
good day.
Yep. You too.